Hello and greetings. Today we are going to take a look at everything you need to know about waves at this point in the school year. So as we jump into this, just make sure that you're um, deciding on what you need to ask questions about. What concerning this do you not understand? And then I will be able to address whatever those questions are. I do also want to remind you that this presentation will relate directly to your quiz. So the first question here is, what happens to wavelength as the frequency decreases? So we need to remind ourselves that when we look at waves, there are two important characteristics of waves. And the first is going to be what we call the wavelength. And just to show you what that looks like, you want to measure from two identical parts of the wave. So here we have two crests. I'm going to measure that distance. And let's say for just example that this distance was 2 meters. And there's another part of this wave speed formula, and that is going to be the number of waves that occur within a given time frame. So let's say that if we're looking at this entire set of waves and we're observing this, this is how many waves pass by, we'll say, this point in 1 second. So this is 1 second of time. And that is called frequency. And the number of waves that pass by in 1 second is going to give us a measurement of hertz. So here, if we're looking at this for 2 seconds, for 1 second, we see two waves pass by. We're going to say that the frequency here is going to be 2 hertz. Hz is the abbreviation. And again, we said that wavelength that we had was 2 meters. Now, there's one thing I want to say about wavelength, and that is, instead of writing the word out because it's really long, what physicists and other scientists will do is they'll use a symbol that looks like this. And this is the Greek letter lambda. So when we want to write this formula, our formula is velocity equals lambda f. Now, again, that measurement needs to be in, the wavelength has to be in meters because that's the SI unit, and the frequency has to be in hertz. So in our example here, what we would have was we would have velocity would be equivalent to 2 meters times 2 hertz, which would give us a total of 4 meters per second. That would be our answer to that question. But again, the wave speed formula is lambda f, where lambda is representative of the wavelength. How do you measure wavelength? That should be the distance between two identical parts of a wave. So we have a couple of examples here. So let's take my transverse wave again. Keep going with this. I can measure from trough to trough, or I can measure from crest to crest. Both of those would be a wavelength. In terms of a compression wave, and this is a horrible drawing of a compression wave, I apologize. I can measure from the center of the rarefaction to the center of the other rarefaction, or I can measure from the center of the compression to the other center of the compression. And those would both be wavelengths. It doesn't really matter whether you choose to measure from a crest to crest or trough to trough or compression to compression. It doesn't matter as long as you are measuring two identical parts on that wave. As long as the parts are identical, you are good to go. What type of wave can transfer energy without a medium? And that is going to be, first of all, let's go ahead and define medium. So in physics, a medium is any kind of matter that the wave travels through, solid, liquid, or gas, any of those. But when we want to look at the kind of wave that does not need a medium, that would be electromagnetic. So all electromagnetic waves can travel without a medium. And I want to just remind you that these are going to look transverse, although they're very different from the other waves, which you'll see later. But when these waves move, they are moving in that transverse pattern. And something else to know about these is, we start out with radio waves, which are really large. Then from there we have some microwaves, infrared. This is basically going to be when you feel heat. The heat waves are infrared. And we have the colors of the rainbow. Then we have ultraviolet, sometimes called UV. This is why you need to wear sunscreen. Okay, so this is that light from the sun that can damage your skin. And then we have X-rays, and we have gamma. Now, the one thing I want to say is that these three right here, these can actually be dangerous to you. When you go to the dentist and they take, X-rays of your teeth, they'll put like this jacket on you that's like really heavy, and that's just to prevent other parts of your body from receiving that radiation. Again, that's one thing I want to also say. Sometimes this stuff is actually called radiation because it travels through radiation. So all these, if you go back to heat transfers, it's kind of connected to this because all this energy will travel without the need for matter. So this is all radiation, not convection, not conduction. Now, you can see some of this, and the radiation or the electromagnetic energy that you can actually see is right here. It is the colors of the rainbow. So this is also called visible light. So you can see this, all these colors. You cannot see anything outside of this range. Some animals have a spectrum of vision that is a little bit higher or lower than this. They can see some things we cannot see. But just so you know, this is just what humans can see. So, all right. Transverse wave moves, or the particles move. We'll say the particle. Erase that. Particles move. There we go. Particles move. This word, perpendicular, that's a geometry word, to wave direction. So let me just show you real quick. Just draw a transverse wave for you. All right, here we go. Going up and down. All right, so here's what's happening. The particles are moving up and down, but the wave is moving left and right. And so it does not move in the same direction. So this stuff, you can kind of see, like if you watch water waves coming in, if there's like a leaf sitting on top of the water or a little toy boat, you'll see that it kind of bobs up and down as a wave is moving. And that is because of this word, perpendicular. So just looking at what we're talking about here, wave is moving left and right, horizontally, but the particles are moving vertically, up and down. Longitudinal wave is different. A longitudinal wave, the particles move parallel to wave direction. So if I just quickly draw a longitudinal wave here. And again, I'm not very good at drawing longitudinal waves, but the wave direction again is horizontal. However, the particle direction is also horizontal. And so it moves like parallel lines. The energy and the particles are moving in the same direction. Great example of this would be a sound wave. Sound waves are longitudinal waves. Now, one thing I do want to say about this is that longitudinal waves, every single longitudinal wave is mechanical. There is no such thing as an electromagnetic longitudinal wave. They do not exist. What is a compression? Well, the first thing is going to be, let's go ahead and write down some facts here. The first thing is it's on a longitudinal wave. Sometimes some of your textbooks or some of your resources as you go into high school physics, some of your resources will refer to longitudinal waves as compression waves. But it's going to correspond to a crest on a transverse wave. So it's like when you have the transverse wave, the compression is like the crest. Okay. It is the part where particles are closest on a longitudinal wave. Okay, so if we look, like let's say here, these are compressions. You got 3 of them for you right there. Okay. What is the amplitude of a wave and how is it measured? So let me go ahead and start with that longitudinal wave. That amplitude is going to be from the center point right here to the top. And if I look at a transverse wave, before that wave began to move, there was matter just kind of sitting here. I'm drawing this dotted line. We call that the rest position. And this is where the matter is not yet disturbed. As a wave is traveling down, basically the particles start here where my red line is, and they move away from that. So you could measure the amplitude right here, or you can measure the amplitude right here, because the definition of amplitude is distance of, we'll say particles from rest position. Okay, now one thing I want to say is that the amount of amplitude and the amount of energy in a wave are a 1-to-1 correlation. So more amplitude equals more energy. Okay, so more amplitude equals more energy. Let's just make sure we have that down. All right, draw a transverse wave and label the parts. So as I want to draw this wave properly, I'm going to just start with like making some lines like this to kind of guide my my pen as I draw these. And I would encourage you to do the same. That just makes it easy if you do that. And you just want to make some lines and kind of curve them around these areas that you indicated. Okay, and then I like to draw the rest position too. I'm going to go ahead and put that right here in the center, and then I'll label it. I do this even if I'm not asked to, but you can see the directions are saying that you need to draw it. So rest position is right here. Okay. I'm going to switch colors. We go to green. And as I go up here, whoop, made a mistake. Let me erase that. There we go. This is a trough. And we have a couple of them. We'll go ahead and label both. We have some crest. You can see right here we have a crest. We have another one and another one. Wavelength. Geez, I need to switch that color. Let me go to black here. So I'm going to say from here to here is wavelength. And hopefully you remember the letter that we use for wavelength. It's a Greek letter. We don't really use it anywhere else in our studies, but we do use it here. It's a little upside down Y, and the name of that letter is a lambda. I'm going to go ahead and draw that right there. The amplitude is, I could go from the middle to the crest, go from the middle to the trough. But both of these are going to be what we call an amplitude. Remember, it's the distance from that rest position. And it looks like I have everything there for that one. Now, one thing I want to go ahead and tell you right now is that even though electromagnetic waves do not use a medium to travel, all electromagnetic waves move in a transverse pattern. Now, one thing about electromagnetic waves that makes them a little special is that we'll have what we call an electric field, and then we'll have what we call a magnetic field. And the magnetic field is going to be kind of sideways like this, whereas the electric field is going to be up like this. And so they have this like kind of like perpendicular format as they move. They move together, but it's really two waves in one. And they're kind of neat. But just remember that all of your electromagnetic waves are going to be moving in a pattern that makes them look like transverse waves. Okay, so I'm going to go ahead and draw a compression wave here. And again, you know that I'm not very good at this, but I'll do my best here for you. Now I'm going to go ahead and tell you like all the stuff that you kind of have, with the exception of crest and trough. You know, you have amplitude, you have all those things on a longitudinal wave. The same things you have on the transverse wave, with the exception of the crest and trough, obviously. But the compressions, are kind of like the crest. You know, you have that area where you have the concentration of that energy as it kind of pulses and moves. And then you also have that area where you have what's called a rarefaction, where you don't have those particles that are stuck together. They're kind of further apart. than they normally would be. On this, I have two options for wavelength. I could, if I wanted to, I could go from the center to the center, and that would be a wavelength. Going from the center of the compression to the other compression. Or I could go from the center of the rarefaction to the center of the rarefaction, and that would also be a wavelength. Remember that your wavelength should be measured in meters. And remember your formula for velocity of a wave. Just want to make sure I go back to it again. The velocity of a wave is a wavelength times frequency. And what is it we measure our frequency in? We have the number of waves that pass by in 1 second. Remember that unit is hertz, AZ. Sorry, HZ. All right. All right, draw two transverse waves of different frequencies and identify which has the greatest and lowest frequency. So what we're going to do is I'm going to make a box to kind of be my area of delineation here. There we go. All right, and I'm going to draw my little guidelines first because, I'm just telling you, honestly, like this helps you to draw these. Otherwise, you can have a difficult time. Now, I'm going to do the same thing, but I'm going to draw more guidelines. I'm going to draw them closer together. All right, and we're going to go ahead and just kind of like connect them like this. Now, something you'll notice is that my amplitude for these waves is pretty similar. If you look, it's pretty similar. But there's two things that are different here. So we do have different frequencies. So let's say that these waves rather, is just 1 second of time. So here I have 2 hertz because I have 2 waves happening in 1 second. Here I have 1, 2, 3, 4. I have 4 hertz. So I have twice the frequency. Now, one thing I want to say here is that if you'll notice the wavelength, like for the one down here, I have a higher wavelength. The distance from this crest to that crest is about twice as much as it is over here. So before we move on, I want to go ahead and make something very clear. If I look at wavelength and frequency and I were to graph those, or I could switch them around, I could put, like if I wanted to, let's say I have my wavelength and I wanted to change it, want to make it larger, then my frequency is going to be the responding variable. It doesn't really matter which one you put because either one of these could be the responding variable. But if one of these increases, the other one's going to decrease. So wavelength and frequency have a negative correlation. And that's opposite, but I will tell you this. If we look at the energy and frequency, they have a positive correlation. So if I increase the frequency, I increase energy. Also, if I increase my amplitude, I'll increase my energy. And I could also place energy on the X here and the X here if I wanted to. You'd still have the same graph. So here's what I want you guys to get at this point. Wavelength and frequency have a negative correlation, but energy and frequency have a positive correlation, and energy and amplitude have a positive correlation. So what does that mean for us as we are studying this? If one goes up, the other goes up. And that is true for this, and that is true for this. However, if you look over here, if one goes up, the other goes down. And that's true for here and here. Now we just got to understand, like, the one that's the inverse here, the one that has a negative correlation, is going to be that wavelength and frequency. Okay, so that's something I want to say right now so that you guys can keep that straight. I really do think it's a good idea for me to ask that question on the quiz, and I'm going to go ahead and tell you that I think I'm going to do it, because you do need to understand those relationships. And just to summarize this really quickly, you could just simply say in one sentence, wavelength and frequency have an inverse relationship, or wavelength and frequency have a negative correlation. And you can see like an example of what we're talking about right here. If you look, I have a large wavelength right here, but my frequency is less. And here, my wavelength is smaller, but my frequency is higher. Okay, if you look at the hertz over here. All right, let's go ahead and move forward. Create a Venn diagram comparing and contrasting mechanical and transverse waves. You need at least 3 in each section of your Venn diagram. So as you guys have completed this, I know that mine might not look exactly like yours, and that's fine. I encourage that. But let's just look at some things we could say. So on, oh, this is wrong. This question should actually be electromagnetic. You go ahead and change that. All right. Sorry about that. All right, so over here we're going to put electromagnetic. And over here we're going to put mechanical. The one thing they have in common is that they both carry energy. Difference here is that these are only transverse. Over here on this side, longitudinal. Or transverse. These need a medium. These do not need a medium. Both of these have amplitude. Both of these have wavelength. Ooh, messed up trying that little lambda symbol. I'm sorry. Let me try again. Another time. All right, one last time here. All right, and they also have frequency. Okay. Something else about mechanical waves. These are going to involve sound waves. So remember that sound waves are mechanical waves, whereas electromagnetic waves are light waves. As a matter of fact, every kind of electromagnetic wave, they're all the same. Every electromagnetic wave is the same. The only difference is they have different frequencies. So the color red and the color blue are the same exact type of energy. It's just that one has a different frequency compared to the other. That's the only difference. But you might have some additional facts that I don't have on mine, which I'm looking very forward to reading yours. So we're going to go ahead at this point, and we are going to stop right here. But I would like for you to take a chance to take an opportunity right now to take your Venn diagram for this question and share it with people that are around you so that you guys can see what someone else said. Now, you might have made a mistake on yours. You might have something on yours that's not factual, or they might have that. But I would like for you to work together to make sure that your Venn diagrams are the greatest representation of your knowledge concerning waves that they can be.